Okay, tonight we're going to be talking about a strong base, strong acid titration, which the practice problems we did in class today were just the opposite. It was a strong acid, strong base titration, which you might be thinking, well, that's the same thing, but we want to talk about it because there is just a little twist, of course, and it makes a titration curve that looks different than the other way around. So let's jump right into it here. So we have a 0.2 molar HCl is being titrated into 75 milliliters of the 0.1 molar sodium hydroxide. So just to envision it, our 0.1 molar sodium hydroxide, 75 mils of this guy, these are going to be sitting in our Erlenmeyer flask with the HCl being in the burette, and then we're going to titrate that HCl in slowly. So before we start, we're going to calculate the pH before any titration occurs. So this is just going to be the pH of 75 mils of a 0.1 molar sodium hydroxide solution. So let's do that. So remember, in sodium hydroxide, it's going to ionize when we put it in water into the sodium ion plus the hydroxide ion. And because sodium hydroxide is one of our strong bases, when we have a 0.1 molar sodium hydroxide solution, that means we have a 0.1 molar hydroxide ion concentration. So, and when we have a 0.1 hydroxide ion concentration, we can easily just calculate the pH of this. But because it's hydroxide, as we remember, hopefully, because it's hydroxide, we're going to calculate the pOH. So we're going to take the negative log of 0.1, which gives us a pOH of 1, and then the pH, obviously, is going to be 14 minus, oops, let me erase that. It's going to be 14 minus 1, so our pH is 13. So that's our starting point here. So if we take a look at this, a titration curve that we could draw, a graph, with pH listed on our y-axis and milliliters of HCl added here, we'll say pH 7 here, 0 there, and it's kind of a rough sketch, so, and 14 there. So because we're at pH of 13, we're going to start this guy right about there. And so what our titration curve would look like is as we add that HCl, it's going to keep going like that until you hit your equivalence point, which will drop. And then that curve will look like that. And then our equivalence point is going to be right there. Equivalence point, pH of 7. Strong acid, strong base. Now, as we said today in class, the equivalence point is not always at 7, but for this one, it is. Okay, so that's what a titration curve is going to look like with a strong base, strong acid titration, whereas the last night's talk, we talked about the titration curve looking different. Okay, so now we're going to take the same thing and we're going to add in 15 mils of a 0.2 molar HCl to 75 mils of a 0.1 molar sodium hydroxide. So this is similar but backwards to what we did today in class. So what we'll do is we'll start off with is we're going to use the molarity formula to calculate the number of moles of the hydroxide ion, which is what we're looking for here. And so I'm going to take 75 mils, I'm going to divide it by 1,000 mils to turn it into liters. I'm going to plug in 0.1 here, and I'm going to solve it for moles. And when I do that, I get an answer of 7.5 times 10 to the negative third moles of my hydroxide ions there. Do the same thing now with my hydrogen ions. I'm going to take my molarity equals moles per liter for my hydrogen ions, and I'm going to plug in, it tells me I have 0.2 molar, and then I have 15 milliliters divided by 1,000 milliliters. And so I got 3.0 times 10 to the negative third moles of my hydrogen ions. So now what I'm going to do is I'm going to write my net ionic equation. We'll do a little before, after here, and let's plug in some values. So we have 3.0 times 10 to the negative third moles. For my hydrogen ion, we have 7.5 times 10 to the negative third moles for a hydroxide ion. So obviously we're going to subtract the smaller of the two, so we're going to subtract 3 times 10 to the negative third here, 3 times 10 to the negative third here. And so it's going to consume all of the hydrogen ions, and we're going to end up with 4.5 times 10 to the negative -3 moles of those hydroxide ions left over. Now there's a couple things that are very important here. One is we need to make sure that we identify we have some hydroxides, which means when we negative log our molarity, it's going to give us POH, which we'll subtract from 14 to get pH. So the next thing we need to do, and this is something that students often forget, as well as teachers like me, is we need to convert back to molarity. So I'm going to take the number of moles of my hydroxides that are left over. So we have 4.5 times 10 to the -3 moles, and we're going to divide them by the total volume that we had. So we, just to scroll back up here a little bit, we had 15 mils and 75 mils added together, so that gives us a total of 90 mils, which we're going to divide by 1,000 mils to convert it to liters. Because once again, remember, molarity is equal to moles over liter. So I have moles over liter now, and that's going to give me my molarity. 5.0 times 10 to the -2 molar is what I get, and that is the concentration of the hydroxides. So to get POH, I'm going to take the negative log of 5.0 times 10 to the -2, and that gives me a POH, and then I'm going to take that answer and I'm going to subtract 14 from POH, and that gives me an answer of 12.70. Okay, so that's my ultimate answer there. So kind of going back up to that graph real quickly here, 12.7. So as you can see on this graph, milliliters, we had added about 15 milliliters, and so we still had not dropped down very much from our starting pH. We won't drop down, we won't have this real big drop until we get to that equivalence point. So here's my question for you to ponder tonight, using all the same information as above. Calculate the pH when 45 milliliters of HCl is added to 75 milliliters of the NaOH. And we'll use all the same concentrations. We haven't changed any concentrations from above. So there we go. That's it.